Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 4 from the June 2024 M1 International A-Level Edexcel paper. And this question here is about, I think, moments. It says a non-uniform rod AB has a length of 6.5 meters. Now, the word non-uniform means that the center of mass acts in a position which is not in the geometric center. If it was a uniform rod, then the center of mass would be taken to act exactly halfway along its geometric center, halfway along its length. And it has a length of 6.5 meters and a mass of 1.2 kilograms. The center of the mass of the rod is 3 meters from A. The rod rests on a horizontal step and overhangs the edge of the step C by 1.5 meters as shown in figure 2. The rod is perpendicular to the edge of the step. Okay, then it says a particle of mass 4 kilograms is placed on the rod at B, and another particle whose mass is m kilograms is placed on the rod at D, which is where AD equals 0.5 meters. Then it says the rod remains in equilibrium and in a horizontal position. Okay, so it remains in equilibrium. That's a key word here. Find the smallest possible value of m. Okay, so I've got the diagram over here so that I don't have to keep scrolling up and down when I am doing my calculations. So first of all, we're told that the center of mass is 3 meters from A. Okay, so let's just get some of these lengths here sorted out, to make sure that we understand properly. So this is 6.5 meters. So from here to here is going to be 5 meters. 6.5 minus 1.5 is 5. That's 5 meters. Okay. And we're told that the center of mass of the rod is 3 meters from A. So 3 meters along here. So that's about here. So that's where the center of mass would be. You don't have to do it, you don't have to measure the length or anything, but that is going to be the center of mass. So that's where the weight will act. The weight will act somewhere over here. Let me just fix this in place so that it doesn't get messed up. Okay, so that's the mass, and we know the mass is 1.2 kilograms. So the weight is 1.2 g. So that's where the mass acts, and that distance was, as we mentioned, from A to 1.2. That's 3 meters. So here we have 3 meters. And then it says a particle of mass 4 kilograms is placed on the rod at B. So over here. So you're going to have a particle of mass 4 kilograms, which will be suspended at B. Okay. So that's going to be 4g newtons. Okay. And then it says, and another particle whose mass is m kilograms is placed on the rod at D, where AD equals 0.5 meters. So AD is 0.5 meters, so that's 3. So like somewhere over here, you can say that's going to be the place where D is. That mass we don't know is mg newtons, and that distance we do know, it's 0.5 meters. So that's 0.5 meters. So that's some of the information that we have. Now, there's going to be a force that's acting vertically upwards over here, the reaction force, which is going to be acting vertically upwards at C. Why will there be a reaction force at C? Because C will be like a pivot. Now, once the situation they're asking says the rod remains in equilibrium in a horizontal position, but we want to find the smallest possible value of m. Now, supposing m wasn't there. If m wasn't there, if this force and this was not there, they weren't there. If we took those away, then the particle would tilt about C. C would be the pivot. So we want to find the smallest possible value of m. Okay, the smallest possible value of m, which will be such that it keeps the object in equilibrium. Just about. It's just about to tilt, but the m there is stopping it from tilting. So that means there's no kind of reaction forces, it's like it's almost out of contact with this step now. It's about to lift up from the step. So there's no reaction force at all in this whole region where it's in contact with the step. It's about to lift up. The only reaction force now will be on the edge of the step. Okay, so that will be R. Now, we cannot find what R is directly because we don't have this mass. I can't say R is equal to this plus this plus this. Well, I can say that, but then I have two unknowns. So whenever you have an unknown that you don't need to deal with, and you don't want to have it in your equation, because we don't need to find I, we need to find M, then that should be the idea that you should have from there, is that that's where we should take moments about. We should take moments about this point, which is point C, because the reaction force will have no turning effect on that, and we will be out of our equation. Okay, and the only values we need to deal with, therefore, would be M and the forces that we do know. So I would suggest that we take moments, taking clockwise as positive, about the point C. Okay, so let's look at the clockwise moments. If this is the pivot, then this side will be like clockwise, and this side will be like anti-clockwise. These two forces will make it go this way, this force will make it go that way around the pivot. So the clockwise moments about C are 4G times this distance here. So we need to know this distance here. Okay, we need to know this distance from here to here, which we know is 1.5. That's given to us. So that's 1.5, and that's equal to, and we got the distance between these two, which is 1.2G times, now we got to find the distance between these two. Okay, so we can see that that's 5, that's 3, so that must be 2. It must be 2 meters here. Okay, because from here to here is 5, from here to the center of mass is 3, that must be 2. So 1.2G times 2, and plus, because it's also going to be anti-clockwise, it'll be on this side. And from C to this point, well, that's going to be 5 minus 0.5, which is going to be 4.5. So it's going to be plus mg times 4.5. Okay, that's the distance from there to there. That's going to be 4.5. Okay, so the only thing we don't know is M. So if we look here, there's G in every single term, so we can cancel out the G's. 4 times 1.5 is 6. 1 point times 2 is 2.4 plus 4.5 times M. So we have 6 minus 2.4, which is 3.6. 3.6, that's right, equals 4.5 M. Therefore, M is going to be 3.6 over 4.5. Okay, yep, 3.6 over 4.5, and that's going to be what? That's like 4 over 5, yeah? So it's going to be 0.8 kilograms. 0.8 kilograms. Okay, so 0.8 kilograms will be the mass that we have to place here to keep this in equilibrium. Okay, so that concludes part A of this question. Okay, now for part B of the same question, what it says here is the particles at B and the particle at D are now removed. Okay, so let's get rid of these two. So this one is gone, and this one is gone. Okay, so there's no particles at D or B anymore. So I don't need this. Do I need this? I don't think so. What was the 4.5? Yeah, I don't need that anymore. Okay, so those two particles have been removed. Now, a new particle is placed on the rod at the point E where EB is 0.9 meters. Okay. So E to B 0.9, that's 1.5. Half of that would be 7, so it's going to be somewhere over here. I don't know what that's doing there. That over there. Okay, so we have, this is, right, they didn't tell us the mass of the new particle. I'm just going to call it just mg. All right, I don't know what it is. It didn't say anything about the new particle's mass. It says the rod remains at equilibrium. Okay, I think this is from before this thing. Last question, let's get rid of it for now in case. All right, the rod remains in equilibrium in a horizontal position, but is on the point of tilting about C. So again, now it's on the point of tilting again, but now what's causing it to be on the point of tilting is this, the weight here. There's no weight here anymore. There's no weight here stopping it. It's just this weight here, which is stopping it from tilting. And this distance, as we just discussed, is 0.9 meters from the edge of the B. This is the point E. Okay, so now, we need to find R. We need to find R. We don't know what M is. Okay, so the sensible thing here to do, because we want to find R and we have an unknown here, is I would take the moments about E. All right, now you can take moments about any point you want to on or off the diagram. And if the thing is in equilibrium, which it is, then the clockwise moments about whatever point you choose must be the same as the anti-clockwise moments. That's always going to be true. So I can take the moments about A, about this point where the weight acts, about C, about B, about any point I want to. Now I'm going to take moments about C. I'm going to take moments about the point about E. Why? Because I don't need to know what mg is. I need to know what R is. Okay, the force acting on the rod at C. I need to know what that is. And that will be my only unknown then. I don't have to consider this force then, because we're on the place where we're taking moments about. So if we take moments about E, if you think about it, you have the force acting upwards here and downwards here. So this would give you clockwise moments if this is the pivot. That would give you clockwise moments. So you're going to have R times the distance between R and that force, which we can work out. It's going to be basically this distance here. That's going to be 1.5 minus 0.9. What's 1.5 minus 0.9? That's going to be 0.6. So that's going to be 0.6 meters. Okay, so we have the distance here is going to be R, the force, times 0.6. And that's the clockwise moments, and that's equal to the anti-clockwise moments will be this one, 1.2 g times, and that's 2 and 0.6, 2.6. Okay, because the distance from there to there is going to be 2.6. This distance here. Okay, because it's that plus that. Okay, so that's basically it. You can find R now. Pretty simple. So R is going to be 1.2 g times 2.6 over 0.6. So we're going to have 1.2 times 2.6 times divided by 0.6. And I'm going to leave the g as in terms of g, so we'll get 26 over 5, which is 5.2 g newtons, which if you want to round to 3SF, without the g, times 9.8, that gives us 50.96, which you should really round to 51.0 newtons. I would leave it like this. That's fine in terms of g. Okay, so there we have the answer to part B. Okay, very, very simple. Okay, so basically this is on the point of tilting about C, but it's in equilibrium. So the reaction force will only be again at this point here. There'll be no reaction forces along this edge whatsoever. Okay, and we want to find the value of R, so we take moments about the thing that we don't need. I don't need to find M here. I need to find R. So I'll take moments about M, where M is, about E, then the only unknown would be R, and the clockwise and anti-clockwise moments are the same. We always find the distance from this pivot, and there we have the answer. Okay, that's part B, and I think that's the end of the question. Other questions from this particular paper can be found in the playlist that will appear on the top right of the screen at the end of this video. Other questions about moments in P1, in M1 will be found in the playlist over here. You can subscribe to the channel by clicking on this link, and the playlist up here will, the video up here will show you how to use my channel to find the things you might be wanting to find. Thank you very much, and see you.